Cool. So we started recording. I'm going to go ahead and share my screen and we can get started on the presentation. Cool. Okay. Everyone, can you see this?
Yeah, looks good.
All right. So let's go ahead and get started. So today we're going to be talking about sorting and searching. This is your 8th lesson, and final lesson next week will be more of a summary across all the different topics that we've gone over so far. Wentel will be doing that one. So Marcus, you want to introduce yourself?
Yeah, can I pop to the next slide?
Is it not showing that? Oh, it says pause. Sharing is paused.
I think I see a static part of your screen.
Okay, let me just stop sharing and restart. I think it got confused because I changed which monitor it was on. Okay.
Perfect. Yeah, hey everyone, I'm Marcus. I'm a engineering manager at a startup called EDO.
Sorry. Okay,
yeah,
cool. Should be good now.
And yeah, excited to teach searching and sorting. I really enjoy kind of algorithm problems, interview problems. You might have seen me post a bit in the coding challenge channel. But yeah, excited to go through. And if you have any questions afterwards, feel free to reach out to me either on Slack or my email address is there.
Yeah, my name's Arnav. I'm a software engineer also at a startup called Sightline. I graduated from Illinois back in 2018 and been part of this program for the last 3 cohorts, as has Marcus. And yeah, I'm also excited to teach the lesson today and always open to helping out. You can shoot me a Slack message anytime, or my email is just my first name at sightline.com. So you can always shoot me an email as well. Cool. So we're going to go through a few different things today. A couple different sorting algorithms that Marcus will go over, a couple searching algorithms I'll go over, and then 3 different interview examples at the end. Yeah. So Marcus, go for it.
All right. So let's talk about sorting. So hopefully this is a concept that people have seen and used before. But let me just kind of give a formal definition of sorting to describe what we're trying to do here. So the motivation of a sort is that we're given a collection of objects and we want to sort them. So to do this, we need objects that we can compare. So usually we'll always want something that you can take 2 objects and say one of them is less than the other one. So an example of something you might sort would be you have a set of dates and you want to sort them from earliest to latest. Or you might want to take a dictionary or list of words and alphabetize them. So all the A's are first and all the Z's are at the end. Frequently when you see sorts, it'll be using numbers, especially arrays of numbers. And most of the examples we're going to go through will be exactly that. But one of the key things to remember is that sorting can apply whatever the object's being sorted. Maybe you have people and you want to sort them by height. There are plenty of examples and a lot of the same principles are going to apply. And then one last thing to note is that sorts can be either in place or out of place. This is true for lots of other algorithms as well, but the key difference is, do we want to modify the original array or do we want to return a new collection that is in order? It's relevant to know that some languages implement their kind of base library search sort in place, and some languages return a new one. So that would be out of place. Whenever you're interviewing, you should probably know which of those your language does. Cool, so let's start off with selection sort. So selection sort is a relatively simple sorting algorithm. What we're going to do is, given an array of numbers, we're going to first look through all of them and find the smallest one and move that to the front. Then we're going to go through and find the second smallest one, move that to the front, and keep going until we get to the end. So you can see a little example here. We find the 1 first, swap it to the front, then go through, find the 2, swap that to the front, find the next one, which is 3, swap that to the front, and find the 4, and now we are done. Our array is sorted. So we have some pseudocode here. And this is basically what we saw there. So we iterate with our loop variable I, going from 0 to the length of the array. Then inside that loop, we're going to go through the array again, starting at I plus 1. So initially, I is 0, representing the start of the array. We start, and our goal here now inside the inside loop is to find what is the smallest element in the rest of the array. So we will loop through the entire array, checking every element in the array. If the one is smaller than our current index of min, then we store that as our index of min. Now that we found the smallest element in the rest of the array, we're going to swap it to the front. And we'll keep repeating this for every position in the array. So the question here is going to be, what is the runtime of selection sort? Does anyone have ideas about how we might reason about this? And feel free to unmute yourself and talk. Feel free to chat. Or if nobody says anything, I'll be a little bit sad and then go on to the next slide myself. All right, let's go ahead and go to the next slide. So to analyze the runtime, I think there are 3 questions that can help us think about it. So first, how many operations are there in each pass through the array? So in other words, when we are, so initially we're going to try to find what is the very smallest element in the array and put that to the front. So what would the runtime of that? We're going to basically search through the entire array, find the smallest one. What would be the big O of that operation?
Because it could be linear, because like the smallest one could be at the end of the array, right? In the worst case.
Yeah, exactly. We'll have to do a full pass through the array, which will check every element in the array. So that will be O of n for that first run. Now, what about the second time we do the run? So in other words, we found the smallest one, put it to the front, and now we're looking for the second smallest one and everything left in the array. How many things, the first time we had to look at all n in the array, how many are we going to have to check this time?
Just n minus 1.
Exactly, n minus 1, because we've already pulled one out to the front, so we don't need to check that one. Then in the second run, we'll have to look through n minus 1, then n minus 2, then n minus 3, and all the way to the end. Now, how many passes of the array are needed? We're basically going to have to do that for every position in the array. So there's going to be n there. So go ahead and go to the next slide. Yeah, so as we said, for the first pass, there are n operations, then n minus 1 operations, and so on until 1 operation. And then in the worst case, we're going to need n passes. So we get something that turns out to be n squared. So if you sum up n plus n minus 1 plus n minus 2 all the way up to 1, that's going to work out to O of n squared. And this is a pretty common pattern. If you're iterating through an array, and you're iterating through n the first time, n minus 1 the second time, n minus 2 the third time, and all the way through, that's going to work out to a O of n squared algorithm. Are there any questions about that before we move on? Right, great. And again, feel free to unmute yourself or feel free to type in chat. All right, so that was selection sort. Selection sort, I think, was great for kind of a more straightforward algorithm, but it is O of n squared. So we're going to see if we can do better. And that brings us to merge sort. So the idea of merge sort is that it's going to be a recursive algorithm. Our base case, as we should have for every recursive algorithm, is that if our array has 0 or 1 elements, then it's already sorted, so we can just return it. But what if we have a longer array, one that has 2 or more elements? What we're going to do is we're going to take it, split it in half, and recursively call sort on each of those halves. Once we get those halves sorted, we're going to merge or zip those two together. And to do that, we're basically going to pluck out, for the start of the two lists, we'll take the smaller one, put it to the front. Now take the new two list, move the smaller to the front, and keep doing that until the initial lists are exhausted. So we're going to be able to see this right here. So we have the two subarrays. We're going to compare 1 and 2, take 1 because that's smaller, compare 3 and 2, take 2 because that's smaller. And we keep doing this, taking the smaller of the front of the two arrays at every step until that they're all merged together and we have the sorted list. So the key thing here is that this is going to be recursive. So we're starting with this initial big array of 8 elements. We're going to split it right here into 2 arrays of 4 elements, recursively call sort on that, which will then in turn break all of those up. But once we get the results from those recursive calls, we'll have 2 sorted arrays of length 4, and then we just need to merge them together to get our final result. So if you go to the next slide, I think we have some visual representation here. So we see here, we're given a list of 7 elements with the goal to sort it. We start at the very top and we're going to split it into 2, one with 4, one with 3. And we're going to recursively call sort on each of those. That in turn will split those up into 2. Then they get split up until now at this middle row, we're all down to 1 element. And this is where the recursion starts to return. So then at the very left, we have 38 and 27. Those get merged together. 27 is less than 38. So we get that new array of 27 and 38. Then 43 and 3, same thing, 3 comma 43. Now, when those get merged together, this is kind of the first example of seeing a more advanced of this merge step. So we compare 3 and 27. 3 is smaller, so we move that to the front. Then we compare 27 and 43. 27 is smaller, so we move that. 38, 43. So we're kind of merging these, walking through these arrays and merging them together. And then, of course, the same thing's been happening on the other side. And at the very end, now we have this array of 4. We have this array of 3, and we can do the same merge step to get our final result. Is there any questions, actually, before we move on? Are there any questions about what this is doing or how the recursive step is working? I know we only went over recursion, I think, 2 weeks ago, maybe. So feel free to ask if there's any questions about that.
I was just wondering, how do we make sure not to create different arrays? So when we split the original array, we split it into 2, but making like another copy of an array to then populate it with the second half, that can be very costly. So how do we prevent that?
Yeah, great question. So I think there are kind of 2 answers. So one is if we just go ahead and make a new copy of the array, the runtime won't be changed. It'll actually still be the same runtime. We'll talk about runtime in just a moment. It will mean that we take on an additional space cost. So the amount of space we'll use will be more than otherwise. So remember when we talked about in place versus out of place? I think if you're doing an out of place algorithm, which is that you're returning a new array, then you're fine kind of creating the new data structure, a new list, but you're right, that will impose a space cost. If you wanted to do it in place, which is without any extra memory, there are ways to do it. It gets a lot trickier, but basically what you do is you do your recursive step by passing in the array of indexes that should be sorted. So in this case, this first call would call recursively merge sort on the indexes from 0 to 4, and then also call merge sort on the indexes from 4 to the end. You do that merge sort, and then when you need to do the merge step together, you have to do, this is a tricky step, but when you need to zip things together, you're kind of going to swap things around. So when you want to take, you have your left array and your right array. If you want to take the right array and move it in, you're going to have to do a lot of swapping and keeping track of exactly what's where, which is how it gets tricky. There are ways to do that still in the same runtime. I'm not going to go into that here. I can post some links to what that would look like afterwards.
No, that makes sense. I can see it where you would keep track of basically 4 different indexes and just use those to, yeah, sort this around. Yeah, thank you.
Cool. Good question. All right, let's see some pseudocode. And one thing that's nice about this is because we're doing things recursively, the pseudocode is pretty nice. So we have our base case, as we should have for any recursive algorithm. If the length of the array is 0 or 1, then basically the array is already sorted, so we can just return it. Otherwise, we're going to here get the index of the middle of our array, split it into 2 arrays, left array and right array, recursively call merge sort on the left array and the right array, and then merge those 2 together. So the pseudocode, we would want to write another function for that merge step, but that'll actually be one of our interview problems later on. So we'll talk about it more then. All right, so runtime analysis. So recursive algorithms can sometimes be a little bit tricky to reason about the runtime, but let's see if we can take a shot at this. So first off, and I think this is a great question, what is the runtime to merge 2 lists of size n? So if we have a list of size n that is sorted, a list of size n that is sorted, and we're doing the step of taking the smallest, taking the next smallest, zipping them together into a single result, what will the runtime of that be?
Well, if you look at the drawing that you got going on there, every single step you take until you get to everything being separated, you always have things you always have things. So you always divide by 2, and then you put things together at the end. So I think that the runtime has to be somewhere in the logarithm section part of the graph.
Yeah, I think that's a great insight, and that's definitely correct. I think just looking at one step of this, so if you look at the very bottom where we have this array 3, 27, 38, 43, and 9, 10, 82, and we're merging those together. So this is kind of just going from the second from the bottom level to the bottom level. What will be the runtime just to do that one merge step? So we have an array of length n and another array of length n, and we're merging those together into a single array. What's the runtime just for that step?
Would it be log base 2 of n?
And what?
I'm thinking because you're taking the 4 thing, right? Those 4 elements, and you just put them together into like one block, and you basically just combining them. So would it be like log base 2 of n?
Yeah, I think so again, I think I'm saying that we just have 2 sorted arrays, each of length n, and our goal is just to zip those together. So if we have array of length 10 and an array of length 10, and our goal is to merge those together into a single sorted array, how many operations will we have to do? So you're right that log will be involved as we start splitting things in half, but just for that one step.
Yeah, I think for that one step, I think it would just be. I'm tempted to say 10, although we have 20 elements. I'm tempted to say 10 because you always comparing 2 things, and so you always take care of 2 things at a time.
Yeah, and I think, and again with big O, as we talked about, we're a little bit fuzzy around some of the constants. Is it 10? Is it 20? Is it 2x? Those all are the same in terms of big O. And Valerie, I see you said also, but yeah, Jing as well. So O of n, exactly, because we're going to have to, for each of them, walk through each of the lists. So that one step, kind of going from the second from the bottom row to the bottom row, will be an O of n operation. Exactly. So what about for another level of the tree, from the third from bottom row to the second from the bottom row? So this is trickier because we're doing multiple merges, but each of the merges is smaller and half the size. It turns out for each of those, if you think of the entire level, it's still going to be O of n, because you might do twice as many merges but each merge will be half the size. So you're still going to, in total, have to iterate through n elements. So all this is to say, for every level of the tree, we have to do O of n work. And now the next question is, how many levels of the tree are there? And Dario, I think this is very similar to what you were saying, because at every point to build the next level of the tree, we split the array in half, and then we split that in half, and we split that in half. The number of levels is going to be log base 2 of n. So if we have log base 2 of n levels of the tree, and in every level of the tree, we have to do O of n work, the overall runtime will work out to n times log n. Go ahead and go to the next slide. Yep, and we see that here. Cool. Any questions about merge sort before I move on to this table?
Wait, I'm sorry. Could you explain the levels of the tree again? I'm sorry.
Yeah, definitely. So in this case, if we think about there being 8, like the length of the array at the very top, let's say is 8, then the length of each of the arrays 1 level down is 4. 1 level down from there is 2. 1 level down from there is 1. And once we get to 1, that's the base of the tree, because that's our recursive case. From there, we don't need to break them up anymore. So given n, the length of the array at the very top is going to be O of n, and then there will be n over 2 in 1 level down, n over 4, n over 8. So the total depth we need to go down until the length of the array is just 1 will be log of n.
Okay, gotcha. Thank you so much.
Awesome. All right, so let's do a quick recap of sorting. And I will say there are many more sorting algorithms out there. I listed 3 more here than maybe names you hear. There's bubble sort, there's heap sort, there's quick sort. I'm not going to go into a ton of depth on these. And, quite frankly, you're very rarely going to have to implement sort during an interview. Almost every language has something array.sort or sort array or collections.sort or, something that will do all the sorting for you. But it's useful to know behind the scenes what's happening, especially for big O performance. So almost every language implements sort by using some combination or some form of merge sort and quick sort. So almost every language will do sort in n log n performance. And indeed, that is more or less the fastest you can do a general sorting algorithm. So I think the important takeaway here is that doing some of the naive sorts, like selection sort or bubble sort, you can have n squared performance. But by default, if you're talking about an algorithm and you call sort somewhere in there, assume it's going to be n log n. Most of the time, interviewers will just take that for granted. All right.
I got a question.
Yeah.
So you said that n log n would be the fastest sorting algorithm we're looking at in general, right? That got me thinking about radix sort when I learned that, and using that and having that being a little bit more effective. Would you feel like radix sort doesn't really matter in this context?
Yeah, that's a great question. Sorts like that depend on the values that are passed in. So, and this is probably getting more detailed than what you would ever generally talk about in an interview, but it's a topic I like, so I'll take like 30 seconds and talk about it. So what we're talking about here are known as comparison sorts. Those take 2 objects and compare them. There are other sorts, especially for things like numbers, that use the actual values in there. So for example, if you know that everything you're sorting is an integer in the range 1 to 1,000, then you can do certain things that are faster than n log n. But usually those are not like fully generalizable. it's tough to adapt those for doing things like comparing floating point numbers, where you can have an arbitrary degree of precision, comparing words alphabetically. Maybe they can be adapted, but in general, we're talking, these are comparison sorts. And again, pretty much any language, when you call dot sort, I believe, I don't think there are exceptions, but I think pretty much everyone will do a comparison sort that will be n log n. It is true, though, that if you know, for example, that all of the things you're trying to sort are integers, then you may be able to do better in some special cases.
Okay, so it doesn't matter in this context then, because of the general things that we need. Okay, thank you.
Great. Any other questions before we move on to search? Great.
Okay, we can always come back and do some more questions around sorting and searching at the end. But yeah, we're going to move on to search right now. As Marcus had said, same thing for now. If you have any questions, feel free to interrupt anytime, ask any questions on the chat whenever you want. We can go through that. But yeah, so to talk about searching, very similar in terms of you're usually dealing with a single array. Often they'll be sorted in an interview question because they'll want you to use something called a binary search, which we'll get into in a bit. But essentially, the goal of search here is to find a specific object. This does not have to be just like here's a list of letters, find this letter or whatever. It could very well be like an object, like something you often see is like, here's a list of people, find the person with blah blah name. And so there'll be like an attribute on the object called a name. So you have to search through this list and find the one that's that most fits whatever you're looking for, or find multiple, search for the first 5 names that start with A or something like that. So those are different pieces of search. Yeah, we're basically going to go through very similar couple different searching algorithms and move on from there. So we're going to start with linear search. This one, hopefully you've come across. The idea here is essentially just going through the full list of objects that you have and kind of just going one by one and finding the object that matches whatever you're looking for. So you can kind of see an example at the bottom. There's just a bunch of numbers. This is not sorted, and you're looking for the number 20. So you just go one by one, 10, 50, 30, so on and so forth until you find that 20. And at that point, you return or you do whatever action you need to do given the value you were searching for. Algorithmically, we kind of have it at a high level, but it's essentially just a for loop iteration from start till wherever you find until you find the object. And if you don't find it, you return null. Is there any question about that, or does anyone have can anyone answer what the runtime for that would be?
Linear?
Yeah, so that's correct. Dario said linear. Since we're just going through the entire list from start to finish, we're actually going to be basically just doing this in linear time. The next 2 slides actually go through some questions, like Marcus was doing earlier on, about how this works. If we want to go through each of these, so linear, as you answered, would be the worst case runtime. There is obviously the chance of it being the first object, so that becomes an O of one time, but I'm not going to spend too much time on this one because I think hopefully most of you are pretty familiar with linear searches. It's essentially, going to go through all the elements in the worst case. If we're looking for 40, we go through the entire list, considering an element is O of 1, and the worst case runtime, therefore, is O of n. Does that make sense, everyone? I guess thumbs ups in the chat. Okay, cool. Oh yeah, I forgot Zoom has the thumbs up emoji now. All right, so this one's a little bit more common. This is what you're going to see in a lot of different interviews, and this is where we'll spend most of our time. So we're going to talk about what a binary search is. Can we get thumbs up again to see, have any of you heard of a binary search before? Okay, a few of you. Cool. So we're going to start out with a visual representation. So a binary search, again, you have the same root goals here of finding a specific number or a specific object in a list. However, one of the keys to doing a binary search is that the list needs to be sorted. So as you can see in this example, you have 1, 3, 4, 7, 8, 11, 12, 14, 25, 30, which is fully sorted. If the list isn't sorted and you need to do a binary search for whatever reason, then you can always use one of Marcus's handy dandy sorting algorithms to get there. And so the way it kind of works is the goal of a binary search is to kind of break down a list into smaller groups that you can work with. And so what that means is we know this list is sorted. So if we're searching for the number 14, so at the very top it says search for 14, what we can do is we can actually start out by going straight to the middle. Because the assumption is that by going straight to the middle rather than from the start or end, we'll have a better idea of figuring out which side of this list do we actually need to focus on. We don't need to focus on the entire list, because once we look at the middle and we see 8, and we know we're looking for 14, which is higher than 8, we can actually just say it's, actually looks like it's searching for 12, even though it says 14. So sorry, this is searching for 12, but either way, we know 12 is greater than 8. So that means we only need to deal with the numbers to the right of it, because those are all larger numbers. So now when you look at the second step, we're only looking at 11, 12, 14, 25, and 30. Now we can just repeat that same action, go to the middle number, see it's 14, and say that, oh, we're actually looking for a number smaller than 14, because we're actually looking for 12, not 14. And so when you look at that, we get these two. Then we have 11 and 12. So we're going to go try to go to the middle number again. Most algorithms, when you're looking at the middle, they if there's kind of an even number of objects, it'll go to the smaller, the one to the left, essentially, which is the floor of the division. So this is, you're going to look at the 11 and 12. It's going to find the 11. We know that 12 is greater than 11. So now we only have an array of 12, and we found the number 12. And then if we hadn't found a 12, we could have returned null or whatnot. So essentially the goal here of binary search is that we're splitting a list in half, and then based on which side of the list you want to search on, and then in half again, you kind of just keep splitting it in half until you find the values that you're searching for. Does that make sense? Thumbs ups, thumbs downs. See a couple thumbs ups. Okay, why don't we go in and look at some code then? So, high level algorithm. So over here, might be a lot going on at once. Let's start out with the diagram in the bottom right. So in the diagram, you can kind of see that we again have a sorted list of numbers, and we're now searching for the number 23. And so the way it starts is it first goes to that middle element, the blue one, which is 16, and 23 is higher than 16. So it says, okay, we need to go to the right of that. So now we're only looking at 23 through 91. Then it goes to the middle of that and finds 56. Once again, that's the middle element here. And so we know that 23 is less than that. So it's going to take 23 and 38 as the final list. And 23 and 38, it goes, splits it in half, gets the smaller one, and finds 23. And that's the number we were looking for. So we've searched the array and we found the number. So same algorithm, different numbers. So if we talk about the actual code aspect of this, so what we're doing here is we're initializing, or we're basically starting out with what we need is the first number and the last number of the list. And so you can kind of see in yellow on this diagram, we have these variables that we're talking about. So we're going to initialize h to be the last number, the last index of the list. So we can see that there are 9 numbers, or there's 10 numbers in this list. So we 0 index list. So h starts out as 9 in that second row. Then L always starts out as the first element, so that's 0. And then M, which is the middle, is going to start out as the midpoint of L and H. And so if you're not familiar with the 2 slashes, that generally means taking the floor of the division. So right now we have 9 plus 0 over 2, which is 4.5. The floor means we take 4, which is the floor of a number. You kind of chop off the decimal. And so that's why M starts out as 4. And so that's kind of how we get that first list, or the first set of numbers. Then what we do is, I'll come back to the while condition in a moment. We're going to go inside. We're going to say if X, so X is the number we're looking for, if that's equal to the mth element, so the middle element of the numbers, then we found it. And so that means return M. That's kind of your base case here. Otherwise, you're going to say if the number is higher, then we're going to consider the numbers to the right. If the number is lower, then consider the numbers to the left. So if X is greater than, so in the example here, if 23 is greater than 16, which it is in this case, Then we're going to deal with m plus 1, which is the 5th element, through h, which is the 9th element. If we were searching for like 3, for example, then we'd say 3 is less than 16. So that's the else case. So we'd go from L, which is 0, to m minus 1, which is 3. And so that's kind of how we go through this list. If we can't find the number at the end, then we just return null. And the while condition here, while h is greater than or equal to L, the purpose of that is you just kind of continue going until your h and L essentially converge. And so at that point, you know, if we went back to the previous example, right over here, at one point the list was only 1 element long. So at that point, h and L were equal. And so that's kind of the last point of iteration there, because after that, you can't split the list any further. So does that make sense? The algorithm makes sense? Thumbs ups? Yes. Okay. Looks like we have a few. Okay. So, looks like the runtime analysis already has it written down here. So why don't we talk about the runtime first? So what happens every time we, to the size of the array after each iteration? So in terms of, so we're trying to figure out what the big O runtime is here. So each time, what is happening to the list each time?
It reduces by half.
Right, perfect. And so in this kind of scenario, let's say that let's say that n equals 16, like in this example. How many elements are really being considered in that worst case of where n equals 16, which is the it's one after, or actually not n equals 16, n equals 23 here. So how many elements are being considered when we're trying to find the 23 over here? Over the course of the different iterations, how many different numbers end up getting considered?
I guess it could be 3 or 4 if you don't find it, right?
Right, perfect. So given that's kind of our worst case, where we're looking for a number that just happens to take the entire list, what would you say the runtime for this algorithm is? Any guesses?
Oh, sorry.
Oh, go ahead.
Okay. Would it be log of n?
Yeah, why do you think that?
Well, since you're like having to like have it on each iteration, and we're like not looking at the entire like array through those iterations, that's kind of what made me think, oh, log of n.
Yeah, no, that's perfect. Yeah, so that's actually one of the big benefits of doing a binary search over a linear search. Over here, we're instead of having to go through and do each number one by one in O of n, we're instead taking on half the array at a time. And so it becomes a logarithmic algorithm. And so it's just a log of n algorithm, just as you were saying. So that's kind of one of the big benefits of binary search. And honestly, you can kind of use it in your day-to-day even. I've literally been like looking for something in like a dictionary or something like that. Or I think the example, there's a video we'll send out later on. I think Marcus is saying it's in a phone book, looking for a name, and you can look at the middle, and then you can split from there and split from there, and eventually you find what you're looking for. So, dictionaries are another one you can do this with, but nobody really has physical dictionaries anymore. So runtime analysis is exactly what we just went through. It's a log of n algorithm. We just talked through these exact questions. So now we're going to go through the code a little bit. So we already did the pseudocode, so this will hopefully look pretty familiar. This is just the iterative version of the solution here. Unfortunately, the syntax highlighting isn't the greatest here, but essentially, it's kind of what we just talked about. So we start out with like a low, which is the lowest part of the index. And so that's just 0. The high, which is the end of the array. And then I guess in this case, the mid was initialized inside the while loop, but you could initialize it up here as well as just the high plus the low over 2, taking the floor of that. And then, as we said, if the element is smaller, then our new low is, if the element x is bigger than that middle element, then our new low is the middle plus 1. So now we're looking at everything after the middle. So that's why the low is now just what's on the right of it. If the element is smaller than the array's middle, then we're looking at everything on the left of it. which means that the high is mid -1, so now our low is 0 and our high is the middle, -1. And then at the end, if otherwise you just return the middle of the element if they're actually equal. So that means you found the element. And then if we get out of the while loop, we're just returning -1 as an error here. Does this code make sense? It looks like these comments are a little out of order, but hopefully it makes sense. I see one thumbs up. Any questions? Okay, we're going to jump to the recursive version of this. So I know recursion makes everything a little more tricky to wrap your mind around in the beginning. The code actually is hopefully pretty straightforward, but just because we've gone through the binary search bit, but let's talk about how it kind of works in a recursive flow. So with binary search, there's kind of a few elements that you need to be aware of at any given time. There's your current array, there's your low and your high, and then there's your value that you're actually searching for. So once again, we're gonna just find the X element in the array, otherwise return -1. So the first part here, if the high is greater than or equal to low, so that's kind of what our while condition was earlier. We're saying that low is less than or equal to high. Similarly, we're just making sure that the elements are at most equal. If they're not, then we just return -1. We're already, something's already gone wrong and we're not finding the element. So we get the middle element again, just high plus low over 2, as always. And then we're going to check, is this the middle element? Or like if is the middle element X? If so, then we can just return out. We found the element, so we're returning that index. If the element is smaller, once again, we're going to say that we basically need to look at everything on the left. Now, the way you do that with a recursive question is instead of just updating the variable, we're instead going to change the variable that we're passing back into this function. So instead of having high, like instead of changing the variable high to be mid -1, we're actually just passing mid -1 back in as the high in this recursive algorithm. And similarly down here, if the element is on the right side, then we're going to replace the low with the mid +1. So these algorithms are the exact same. The only difference is that over here, we're changing up the variable high and low from the function header in what we pass into the function, versus over here, we're changing the variables in line in the while loop itself. So this just gives you like a recursive version of this. Does this make sense? Any questions about how the recursion works or how this looks? Thumbs ups? Yeah. Got a couple. Cool. So just last runtime summary. Once again, linear search is O of n, binary search is O of log n. So naturally, the binary search is just much faster and more efficient to find whatever value you're looking for. And you might see binary search in a lot of different ways in interview questions. We're going to go through one today, but just generally speaking, if you're asked to look for something, often the interviewer might be intending for you to look at binary search as an option. So just consider it. If you're looking at, if you're talking about runtimes, and there's a question or a goal of hitting a logarithmic runtime, then the binary search is probably involved as well there. So any questions about search in general here? Okay, so we're going to jump into the first interview example. Marcus, do you want to take it away?
All right, cool. So this is an interview problem. It's actually one that I have asked as an interviewer, slightly modified, but pretty similar, and uses some of the concepts that we talked about. So let's go and jump into it. So the problem statement here is that our goal is to make a combined list from 2 lists. So if we are given 2 lists of words in alphabetical order, we want to return a new combined list that contains all the words from both lists and also is in alphabetical order. So the same word, worth knowing is that the same word may appear in both of the input lists. And if it does, we only want to include it once in the result list. So let's look at an example of what this means. If we have 2 lists, the first list is a list of dog breeds. The second one is I guess, a list of professions that you might see in the Olympics. We see beagle, boxer, corgi, retriever, setter, terrier, and dogland. And we have boxer, fencer, retriever, runner, and setter. So we see both of the first two lists are sorted in alphabetical order. Our goal is to output a single list that is in alphabetical order. So we see beagle comes first and then boxer. Now, even though boxer appeared in both list A and list B, we only want it to appear once in the output. So we only see boxer once, corgi, fencer, retriever, and all the way through. So first off, what concept that we talked about is this? What concept that we talked about is this similar to?
Is the merge sort?
Exactly. This is basically the merge step of merge sort. In merge sort, we would have two subarrays, sublists that we want to merge together in unified order. This is very similar to that. So now, before we go into the full answer, let's look at what some candidates thinking they're really clever try to do. So go to the next slide. They say append list A to list B, call sort on it, and we're done. So I would never hold it against a candidate for trying something kind of cheeky like this, but why is this not the best solution?
How do they deal with duplication?
Exactly. So one issue is that this doesn't deal with duplication. Boxer, for example, would appear twice in the output because they've appended it together, so now it'll appear twice. And then there's another reason. What would be the runtime of this algorithm?
No bueno.
No bueno, but how no bueno?
Because you basically merging both things and then you starting it. You can definitely do better than that. It's pretty bad.
So what would the actual big O be?
I'm leaning towards the square and square.
Okay, so I think there are two steps here. First, there's the step to append them together, and then there's calling sort on that appended array. So I'll say that the cost to append them together will probably just be O of n or something similar. And then what would be the big O of calling sort on that length of n array?
And log n.
And log n, exactly, as we talked about. If you have an array of length n, then calling sort on it using pretty much any default sorting algorithm will be n log n. So slightly better than n squared. We would get n log n performance from this, but we can do better, and we'll see what that looks like. But I wanted to call this out because very much we should make sure we have the intuition that anytime we're calling sort on something of length n, that by default is n log n. Okay, so let's talk about the better solution. Go to next slide. So as we talked about, this is very similar to the merge process of merge sort. So our goal is going to be to do the exact same thing. We're going to keep track of the current index in list A and list B, and we'll repeatedly take whichever one comes first. We'll keep doing this until we reach the end of the list. So that gives us something like what we see on the next slide. So what do we see here? Given list A and list B, we're going to create a result array that starts off empty, initialize index A and index B to 0. So while index A is less than the end of the list and index B is less than the end of list B, then we're going to compare what we see in list A at index A to what we see in list B at index B. If the one in A is smaller, then we're going to append that and increment index A. Otherwise, B is smaller, so we're going to append that and increment index B. So this is the first stab, and I think this generally gets us close. Now, could anyone see one of the issues with this?
I'm just thinking like if one of these lists has like let's say list B has like 3 numbers and well 3 words and list A has more than 3, you could have some inputs missing from the result list, like if, because it checks the length of both to continue. So you have to have maybe another loop at the end to just check if you have everything from both lists.
Yes, exactly. So if we think of walking through list A and walking through list B, we're going to terminate our while loop when we get to the end of list A, but there might still be elements left in list B. And with what we currently have here, those would just get dropped. They would never get added to result. Dario, do you see another issue with this, or is that what you're going to say?
I had a question.
Yeah.
Quick background, I'm more familiar with JavaScript and Python. So this is where my question comes from. I see that in part of your if statement, you're basically checking that one word is less than another. How does that work exactly? Because I know in JavaScript, you cannot just compare two words like that.
Oh, that's a great question. So we're talking about comparing strings, and I'm comparing them as if they were numbers. So this is pseudocode. I think a lot of languages do actually let you just straight up compare, and then whichever one is less is whichever one comes first alphabetically. And I actually do see in JavaScript, I think you can do that.
I'm actually checking right now. I'm doing a console on the browser.
Yeah, I actually just opened up a tab and did that. So I did ABC is less than CD E. Well, and I did find that it returns true for the ABC is less than CDE.
That's interesting. So when I encounter problems like this before, I always engineer a way to compare them. I was not really aware of the fact that you can just plainly compare them like that. Thank you.
Yeah, and if on an interview you don't, for example, know that, I would think most good interviewers should prompt that, and if they see you start writing a helper function that compares two strings, is A less than B, I would think most interviewers would probably cut you off and throw you a bone and say, hey, there is actually, you actually can just do less than. That's not really the goal of this problem. I usually don't like testing whether just a candidate knows some obscure behavior of JavaScript. But yeah, then happy to teach that something. Most things in most languages can be compared using less than. So strings, usually if you do this, will compare alphabetically. Dates, usually if you do this, will compare whichever one's earlier or later. But it is worth checking to make sure that in your language, the behavior is what you'd expect.
Yeah, thank you so much.
Cool. So there is one other issue with this, and I think that this is what Dario brought up earlier with the naive solution, which is that we still don't have anything to handle duplicates. So right now, this algorithm will work great, but we will see Boxer appear twice. So I think we have a fix for that on the next slide. And yeah, how do we avoid duplicates? So go to the next.
Wait, before you go, I was just gonna give it a try. I was gonna try, but never mind.
No. I would go back. Don't show. Yeah, let's see which ideas you have.
Would you this is a direct question to you. Do you think using like a dictionary to keep track of the things you've seen before is a good idea?
Yes, that would definitely work. So I think what you're saying is you could have a dictionary or a hash set, something that has easy lookup to say, here are all the things we've seen before. If we get to something that we've seen before, then we don't need to add it. We could just skip that element. That would definitely work. Runtime, that would be great. What I have here is taking advantage of one other thing, which is that if we have seen it before, then where in the result list must it be?
Previous. Oh, that's hard.
Yeah, it must be the very, basically the thing that we just put in. So if we're, because we're going through these sorted arrays, if we've seen Boxer the first time, we put it into result. The next time we see Boxer, it must be the last thing in result array. So we don't need to store everything in a dictionary. We can just look at the last thing in our results array. So let's go ahead and go, I think, 2 slides forward, and we'll see this. So now we added this check. If result.last is not equal to the element that we're about to add, then we go ahead and add it. If it is equal, then we're not going to add it to our result. We're basically just going to skip it, but we're still going to increment our index. So that way we can make sure we've skipped over it and we won't be adding it to our results array. Now, as Valerie brought up, then the last thing we want to do is make sure that anything left over in our list after we finish the while loop gets added. And so I think I have just one more set of while loops at the end. So let's go to the next slide. Yep, and this is exactly what Valerie said. So we had all of our code from before on top. And then now at the end, once we exit, any remaining elements of each list need to be added on in the exact same way. So I have another while loop while our index of A is less than the end of the list, go through and do this exact same thing. And then while index of B is less than the length of B, go through and do the exact same thing, and then return result. And this should be a fully working solution. All right, any questions about this algorithm? Cool. Let's go to the next slide. And let's talk about the, oh, actually go back. Well, whoops, I showed the answer here, but let's talk about the runtime of this. And this is kind of what I alluded to before, I think when we were talking about merge sort. So, but basically, actually, let's go back to the code. I think that makes it a little more clear. We have this while loop where we have an index in A and an index in B. And those indexes basically just walk through linearly each of the arrays. So the runtime, if list A has length n and list B has length m, will basically be O of n plus m, because total throughout the entire algorithm, all we're doing is walking those indexes all the way through each of those arrays. So this will get basically linear performance. And this is also why it's better than the kind of cheeky append them together and call sort on it, because that would be n log n. Any questions about the runtime? All right, I think that's not a question for us. So let's go ahead and move on to the second one.
I think, Dario, are you able to mute?
Oh, sorry, guys.
No worries at all.
Okay, are there, so last call, any questions for the first interview question? Oh, whoops. Okay, cool. So we're going to jump into a second question. So this is called two sums. So the question here is essentially going to be around finding if there are two integers in a list that add up to a specific, whoops. Okay, moving around Zoom screen is just totally messed with slide selection. Okay, so the question here, so given a sorted array of integers and a target, determine if there's a pair of numbers in the array that sum up to the target. So the question here is there a way for us to get to find two numbers in a list that add up to a given number? Okay, so there's a couple examples. So first one, given the numbers 2, 7, 11, and 15, we're trying to find out if two numbers add up to 9. The output would be true because 2 plus 7 equals 9. The second one, given the numbers 2, 3, 11, and 15 with the target of 9, the answer is false because there are no two numbers in this set that you can add up that will actually turn into 9. So can anyone come up with what might be an optimal way to target solving this? Daria? Do you have a...
I don't know that it's optimal, but I have an idea.
Yeah, go for it.
It's similar to it's basically the sliding window algorithm. So you start index at 0 and 1, and then if the sum of those two values is less than what you're looking for, you move the j. So like the index at 1, you move it to include one more number, and if it's less, then you decrease one number. So you go through it like that.
Yeah. And yeah, and that makes a ton of sense. Do you know what the runtime for that is?
I was thinking linear. What do you think?
Yeah, no, yeah, you're right. Makes a ton of sense. That is definitely a very optimal solution. And you kind of broke the question immediately. So does anyone have any other ideas on different ways to solve this outside of sliding windows, which is totally fine. It's just wonder if there's other thoughts on other ways to do it.
I mean, there's an O of n squared way where you just go through the list twice and match up each number with another number in the list.
Yeah, totally. That's definitely another valid solution. As you mentioned, that's n squared. So less optimal than the sliding window approach that Dario was talking about. There's a lot of ways to solve this question. This is actually another optimal way, but involves using additional space. And this isn't going to be the actual solution we talk about, but the high level here would be you just take all the values, put them into a lookup table or a dictionary, a Python or something along those lines, and you just look for the complement. So for example, with this set of numbers, 2, 7, 11, 15 roll it in a dictionary, you start out with the number 2 and see if 9 minus 2 exists in the dictionary, which is 7. It does, so it's true. With this one, if you were looking at it, you have 2 in there, you see if 9 minus 2, 7's in it, there isn't. You look 9 minus 3, 6 is in it, it isn't. 9 minus 11, -2, 9 minus 15, -6, none of those numbers are in it, so you return false. So this is another solution as well. There's a lot of different solutions to this. But let's think about a solution that does, okay, I guess Dario already gave us one that doesn't use additional space. Let's think about a way to solve this using either sorting or searching from today's lesson. So what is a way we could do that? And it may not be as optimal in terms of performance.
I guess you could use like the binary search, right? Like the array is already sorted.
Yep.
So for each integer that you're looking at, you would, first of all, you'd be looking at it depends on where it is on the array, but yeah, so you'll be looking at the difference between the target number and this integer, and then just searching for that number in the array. So like you start at the middle, and if like the number you're looking for is less than the middle number, then you check, I guess sorry, my sense of direction is really bad. I think it's the left
Yeah.
of the array.
Yep.
And if it's larger than, then you check the right. Then yeah, you just do that until you find it or not. If not, then you go to the next integer. If you do, then you return that, right?
Yeah, and I don't know why you guys are at this lesson. Like you're all killing it. That's the correct. That's perfect. So this is exactly what you just talked about. We've just kind of written down dot binary search because we've already gone over the binary search algorithm a few times. But essentially exactly what you said. So you have an array and you kind of go through the array looking for a specific number, which is the complement of what you're looking for. So, let's say your target's 10. What's going to happen is that when you're going through the array, you do the binary search looking for 10 minus whatever current number you're on. So let's say we're on 3, for example, 10 minus 3. So we're looking for 7 in the array. And if you find it, then you return true, assuming it's not the exact same index you're on right now. Otherwise, you return false. That's correct. And there are small enhancements you can do to this. You can try to only look at the numbers after the I that you're on right now because you've already looked at everything before that. Other small things that you could do to make this a little bit better. but does this algorithm make sense to everybody? Can we see some thumbs ups or thumbs downs or whatnot? Cool. Can anyone tell me what they think the runtime for this is?
So a binary search, as we said, is n log n, right?
Yeah.
And we're
Or no,
doing this
sorry.
n time.
So binary search was actually log n, because we are
Right.
going
Okay.
through and
Yeah.
Yep.
Yeah. Okay. And then we're doing this n times. So would it be n times log n of n?
Yep. Perfect. That is correct. Now let's say that the array we were given was actually not sorted. How would that affect the runtime here?
I don't think it would it?
Why not?
Because a binary search. Wait a minute. I just got myself. Binary search. It requires you to have an order list. Never mind.
Yeah.
But like sorting it will just take n log n. So like the runtime will not be affected, just be the same, even if you sort it and then do this, right?
Yeah, exactly. So that's perfect. So as you mentioned, I mean, this entire algorithm is n log n, and if we had to do a sort before that, because we're not given a sorted array, you could just sort it and it would still be n log n, because it's just 2 n log n, which, you know, you can drop the 2. So that sounds perfect. And that's kind of what we talk about right here. So if we were to sort it, it would take n log n, and then there are n operations that each take log n, so it's n log n again. So overall runtime is still n log n. As was mentioned earlier on, there are alternative solutions that are more efficient than this, but this is just kind of an example of using a binary search in practice here. So any questions about this interview question or anything about this algorithm?
Yeah. Can we go back to the first solution, the optimal one that you presented using the MemoI solution?
Yeah, and this one does use extra space in that it has a dictionary that's being tracked.
Yeah, I was just wondering. So I see that you follow it like a loop, like you use loop to find what you're looking for here. So I was just wondering if you can do recursion and just use the memo and initialize it to empty, and then you populate as you go. So what I'm envisioning is basically drawing out like a tree with every value, and then using a memo, you can just look at a tree very quickly. The front complexity wouldn't change much, but I just think it's a different approach.
So you're saying that you would recursively insert elements into the dictionary and identify.
So not quite. So I have an outer loop, and then I have a recursion solution inside of there, a loop, and so I have a memo object as a parameter that I start as empty, and I pass that parameter to the same function because of recursion. So then it keeps me from looking at things that I've already seen before, and it just saves me from having to do loops.
So I think that might make sense if we were not, so in this scenario, in the way the code is written here, we aren't actually going through the list twice. Is that the thing you're trying to solve, not having to go through the list twice?
I was just wondering if I can do recursion at all.
Generally speaking, you can do any algorithm, like not any, but a lot of algorithms can be converted to recursion. It just might add more complexity. So I think what you're talking about would work. You would be able to pass in, yeah, you'd be able to recursively call it on whatever set of the array that you're working with. Anything that's iterative can be converted to recursion for the most part. So I believe what you're saying is correct. I'm not sure if I have a full grasp on exactly how you're talking through it. Feel free to, like, if you want to write it up and send it in the channel, you can do that. Or I don't know if Marcus had a better grasp on the exact suggestion, but
yeah, so just one thing I'm calling out here. Sometimes we talk about memoization for recursive calls. This memo is not exactly that. This memo is basically an array of what are all the numbers I've seen. You actually brought this up, I think, in an earlier one where you want a quick lookup of have we seen this number? So, you know, another word for memo would be, you know, dictionary of seen numbers. I'm not sure if
I see what you mean. No, I see what you mean in the different use sphere of the memo. I was just wondering, like, altogether, if we can approach this and yeah, I think my question has been answered.
Okay, cool. And don't hesitate, like, even though it's not necessary, like feel free to write the recursive solution. I think practice with writing recursion is always good because it's not the easiest thing to grasp for immediately. So feel free to write it up, send it in if you wish, and we can always, you can tag one of us or tag me, and I can take a look and we can talk through it on Slack. Any other questions about this algorithm or this interview question? Okay, I'm gonna let Marcus bring us home with the third interview example.
Cool. So this one I'm calling square root approximation. And the formulation is pretty simple. If you go to the problem statement, given a positive number n, return the square root of n rounded down to the nearest integer. And to avoid any sort of cheeky solutions, you should not call any built-in square root function in your solution. So for example, the square root of 9 is 3, because 3 times 3 equals 9. The square root of 10 is also going to be 3. The actual square root is like 3.1 or something, but we're going to round it down to the nearest integer. So just return 3. And as a more complicated one, square root of 152423153 should be 12345. So this seems like a lot. There's probably some like very complicated mathematical way to actually compute a square root by hand in a long way. I did not study math. I did not major in math in college. I absolutely don't know how to do that. So given that, does anyone have any ideas for how we might go about something like this? All right, let's go to the next slide and see if that gives us any. I'm going to give us some hints. Suppose we want to find the square root of 2000. Is 10 too large or too small?
So you're basically just testing out numbers to see what would be the square root.
Yeah. So yeah, exactly. We're going to try testing some numbers. We're going to do kind of a guess and check approach. So let's say we're trying to find the square root of 2000 and we guess and test 10. Do we know, is 10 going to be too large or too small?
It's too small.
Yeah, exactly. 10 is too small. 10 squared is 100. That's much less than 2000. Cool. Now, is 100 too large or too small? 100 is too big, exactly. If we square 100, it's way more than 2000. So we can know from this that the answer is going to be somewhere between 10 and 100. Does this give anyone any ideas based on what we've talked about earlier? So let me give one idea we can do. We can, starting from 1, try multiplying 1 by itself and comparing it to the target. So 1 squared, nope, 1's too small. 2 squared, nope, 2 is too small. 3 squared, 4 squared, 5 squared, all the way up. And then at some point, I'm going to quickly look up the square root of 2000, so I don't know it off the top of my head. But around 44, we'll find 44 is too small, and then 45 is too big. And that will give us the answer. We can basically try 1, try 2, try 3, all the way up until we find the first one that's too big. And then our answer will be the one right before that. Does that seem like a similar concept to anything we've talked about already here in this lesson?
It sounds like binary search.
Yeah, so what I just described is kind of like a search. I'm kind of trying to find where the square root of 2000 is. I think what I just described is kind of the linear search. You do 1, you do 2, you do 3, you do 4, all the way up. But you're exactly right. We might be able to do better than that by doing a binary search. So what would a binary search look like here? And the reason I like this interview example is that it's a little bit different. We're not searching through an array exactly, but a lot of the same concepts of the binary search are going to apply here. Can anyone describe how we might do a binary search?
Why don't you start at the middle of a given number and you square that, and if the result is too big, then you go lower, say half of that, and so on and so forth.
Yeah, exactly. So we can kind of test a number. We kind of have a range of possible values. We'll test the middle number. If we square it and we find out it's too high, then we know what we're looking for is in the bottom half. If we square it and it's too low, then we know what we're looking for is in the top half. Either way, we can kind of throw out half of our range. In the exact same way we're doing binary search before, that narrows the possibilities by half, and we keep doing this until we find what we're looking for. So if we go to the next slide, I think I lay out some of the pseudocode for this. So we track a range of possible answers. We test the middle of the range and square it. If it's too small, then we continue searching in the second half of the array. And if it's too large, we continue searching for the first half. Now, what should we use for our initial, and let's say on the previous slide, what should we use for our initial range when we actually start off? What should our lower bound be and what should our upper bound be? So what is a number that we know will be smaller than the actual square root?
So I guess the upper bound would be that number itself.
Yeah, that would be a great upper bound. You know, it's the square root should always be less than the target. Maybe we have one edge case around 1. But yeah, we just need any number that we know is bigger than the actual square root. And so yeah, we can start with a number, or I think I even do the number plus 1, because that will definitely be bigger than the square root. What about for the lower bound? What's a number that we know will always be smaller than the square root?
0?
Yeah, 0. That'll work just fine. We know 0 is always smaller than the square root of any positive number. So we're intentionally casting our net big. There's like very small optimizations we could do here, but we can just do that. This is the beauty of binary search. Because log n is so efficient, we can just take this big range, 0 to n plus 1, and then we're going to start binary searching from there. So let's look at the next slide. So this is very, very similar in structure to the binary search code we saw earlier. So we start with a low and a high. Low starts at 0 because we know that's smaller than the square root of n. High starts at n plus 1 because we know that's larger than the square root of n. And we're basically going to do a binary search here. So while we haven't really found exactly where it is, and I'll talk about this while condition in just a moment, we get the midpoint, we square it, and now we check, are we too high or too low? Well, if mid squared equals n, then we're done. We found the square root and we can just return it. Otherwise, if the square is greater than n, then our number is the number we tried, our mid is too high. So now we need to shrink our range down to high equals mid because we know that's too high, and then we can keep looping. Similarly, if the square is less than n, we know mid was too low. So we take the right half of our range and keep looping. Now, when should we stop looping? When have we found what we're looking for? Well, if we get to a point where low equals high minus 1, in other words, low is adjacent to high, then we know low was too small and high was too large. So therefore, the square root is somewhere between those numbers. And because we want to return the square root rounded down to the nearest number, we return low. That would be our answer. For example, if we're trying to find the square root of 10, we would get to a point where low equals 3 and high equals 4. The actual square root is 3.1 or something, and so we'd return 3. Yeah, any questions about this?
Yeah, I was wondering about, so you have low is equal to 0 and then high is equal to n plus 1. And then the loop is checking high minus 1. I was just wondering why not just use n?
For high equal, so why don't I just start high equals n?
Or even the purpose of that variable high, because you can just use n and keep on using n to make it smaller if you need to. Because I see that n plus high is equal to n plus 1, and then you checking for high minus 1. So you basically adding 1 and then taking 1 to start with. So I was just wondering.
Yeah, so I think, so one thing, and this is a great kind of general advice for whenever you're writing a binary search, it's the issues that always come up during binary search, and I always encourage people to write binary search at some point for practice, is that the concept itself is one thing, and hopefully we all understand the concept, but actually writing the code very frequently has off by 1 errors. And it's really important to keep track, what is each variable doing? So in this case, low is going to represent a number that we know is smaller than the square root of n, and high is going to be one that is larger than the square root of n. And those are going to update a whole bunch as we're doing this loop, but we should always have those conditions be the case. So we should always have it the case that low is too small and high is too big. And that means when we have these conditions here, we know exactly how to update them. So if we initialize high to n, and then, so when we initialize high to n plus 1, that's only the initial, the very initialization, and it only has that value before we're going through the loop. Once we start going through the loop, high is going to be updating to many other values. And so it would actually have different behavior. If we initialize high to n, then we still want our condition to be low is less than high minus 1. We want to keep looping as long as low is not adjacent to high. This condition could equivalently be while low is not equal to high minus 1. We basically want to keep looping until that they've narrowed together and our window is exactly adjacent numbers. Does that answer your question?
Yeah, that definitely helps. Thank you.
Cool. Any other questions about this? Great. Yeah, and I think that the reason this is a cool example is it just shows binary search in a little bit of a different form. Before we talked about binary search like through an array, this is not through an array, so it feels a little bit different, but the same concept is there. The key thing is that we're able to test a value and eliminate half of the possibilities depending on the results of that test. And as long as you have a problem kind of in that form, you should start thinking something binary search, something that can get us log n performance.
So we still have about 1 minute. Are there any final questions or thoughts people had? We do have a couple slides in the appendix that we'll share so you guys can take a look. This is a few visualizations of other types of sorts or some of the sorts you've seen. This is the video we were talking about earlier on that there's a link to in the bottom about how the binary search works. I think Marcus was saying it's a very entertaining video.
Yeah, I highly recommend it just for his kind of antics.
And I think these are the two that we have in the appendix. So,
oh, and then
actually,
one
there's also
more.
this.
Yeah, so I put together a quick list of practice problems. I'll post these, I guess, in the coding challenge channel. But I have some good ones. The first one is just great practice for actually implementing kind of a binary search type thing. And then I have another one that has searching with 2D arrays, one that is a little more similar to the square root one, and then some medium to hard ones if you just found those way too easy and you really want some challenges. Although I will say those last two are pretty tough. If anyone takes them on and wants a hint, I would be very happy to chat with you about this.
Cool. So we're pretty much at time. So if there are no other questions, we can end it here. Let me stop the recording.